Hi everyone.
I'm Dima, the PhD student.
I'm mostly working on trustworthy
The AI at
privacy-preserving AI.
Today I'm going to explain to you what are the challenges with adoption of the said trust.
AI systems. So in general, and this is a very crude overview, the more data you have, the machine learning system is going to be. Obviously, it depends on generalization, depends on
How representative your data is, but the overall the more data, the more potential you have to extract something useful out of it. So to do that,
given the current data privacy regulations such as GDPR or the HIPAA, so this is the Health Product Act, we could potentially devise multiple methods to allow that to happen. So methods for privacy, methods for robustness retention, etc., etc. The point of this slide is to show that there are multiple such methods. Some of them are very difficult to implement, some of them are very difficult to understand, some of them are computationally costly, but they do exist. So encourage more data sharing and more collaboration. We want to try to make sure that
methods that we use to fix the other bits. So the first kind of method, what you do is it's not the broad sets of privacy together. They just track some bad models
which can preserve privacy by default, right? Sounds reasonable. So one of
my earlier work shows that, and it's possible to create models
which are more privacy preserving than the rest by just adjusting which layers you use, which normalization you use, the batch size, etc., etc. So you could technically
protect yourself against
privacy attacks and reduce the privacy leakage, by doing that. However, this is a bit problematic because how do we evaluate how much privacy is leaked? Is there a specific attack that we want to use? How many factors can we change? Every single year we could potentially find a new architecture that's not been used before. What's the field of evaluation of this method? And the problem is, while this is a good idea on paper, it's very unlikely to scale in reality. So the other thing that we could do is we could work with the methods that I've outlined a few slides ago and try to make them work better. So the one that my lab concentrates on is differential privacy. And for those of you who have worked with it would know that differential privacy is very expensive, both computationally and performance-wise. So the models that you train essentially have some noise embedded into them. And as a result, not all of your predictions are as accurate as they would have been without differentially private training. And while we could make it better by adjusting certain things, so how much the noise gets added, what kind of noise we add, at which point of the algorithm we actually add the noise to, the problem is it doesn't necessarily promote the use of differential privacy. So just by making the method better, you don't necessarily make more people adapt it. And this is where we actually elaborate on the two biggest problems of privacy-preserving machine learning. So it's not just that there aren't enough methods to do it. The biggest problem is that people are really not incentivized to use them in the first place, because while it's nice to have access to more data, you're essentially using those methods to reduce the utility of the data you're trying to get access to. And I'll explain that a bit better in a second. So the first problematic area is, okay, we have all these methods and all these technologies, but where do we actually use them and how? So we've just seen this picture. It kind of shows you an overview of where different protective mechanisms can be put into when it comes to collaboratively training a machine learning model. And as you can see, there are a lot of different pictures outlining a lot of different techniques which affect different parts of training differently. A lot of the word different here. But the point is, there are many different places where it could happen, and you're not necessarily very well informed which part should be protected more than the others. So to kind of solve that problem comes my PhD, and I'm working here as an adversary. I'm trying to show where exactly collaborative machine learning fails. So which specific things I can break more easily than the others to show you that we really need to protect those areas more. And the noteworthy example is model inversion attacks. So the intuition is pretty simple. You train the model locally, you send your contributions, and I try to invert those contributions to reveal the data that you used to generate the model update. In literature, this is a very common technique. It's been used a lot. There are really complicated ways of doing it, but the results that we can generate are pretty impressive when it comes to medical image analysis. So on the left side of the picture are the originals. On the right side of the picture are the reconstructions. As you can see, they are pretty privacy revealing because, one of the people in the second picture have breast implants. On the other one, the breasts are just missing. And this is not the information you would want to share with your collaborators. It can even scale to some other more challenging contexts, such as medical image segmentation. So this is the data from the BRATS challenge, which we managed to reconstruct better than the baseline algorithms. So now that we have the places where these algorithms could be integrated into in more context. We also have the adversary that shows what happens if you don't integrate it. We need to find the solutions of how do we give people the tools to do that. So Premier is one of the things that we worked on, which is essentially a collaborative learning platform for medical image analysis, which involves using secure multi-party computation and differential privacy. And in a nutshell, it allows multiple hospitals to collaborate on federated machine learning models and medical image analysis in a secure and privacy-preserving manner. So, okay, now we have the motivation, we have, what happens if we don't do it, we have the tools to do it, and now the most important thing, why would people actually want to invest into it? Can't you just go and, buy more proprietary data and don't really care about all this collaboration part of things? Well, you could, but it doesn't scale very well. So in order to perform better collaboration, we need to actually incentivize people. And one of the ways of doing it is giving them something in return for their contributions. So in order to do that, we need to analyze how useful their data is, how exactly do we reward and how much do we reward those participants? And when they share the data that is more complex, what does complexity even mean? Is it actually improving the model or is it making it hallucinate more? And this is something that we're currently working on. So we're doing a lot of data valuation and a lot of modeled update valuation. So this slide kind of represents if you have access to more challenging data, it's not necessarily more good data, because half of these pictures make no sense. They've just been really bad radiological imaging. Some of those are just really challenging examples that the model should be learning from. So the fundamental questions are, how do we evaluate if your contribution actually made the model better? Do we really want to reward you for this? Or are you just sharing, the crap that you've generated, which makes the model hallucinate more and as a result, has higher uncertainty? Is the data good? Is the data bad? How do we actually evaluate it? And solving this specific challenge is the key to incentivizing more people to take part in this research and then in the production of better models that have been trained on bigger data sets. Finally, one of the other tasks which is very challenging, and I appreciate this is not a very good representative image, but this is just something that I worked on. You really want to integrate other methods into privacy-preserving ML. So this is some of the explainability methods. So this specifically is GradCam. It tries to outline the regions of importance in individual images. And as you can see, depending on the image, depending on whether it's male or female subject, the active region changes. What privacy-preserving learning also does, it could potentially shift those regions of interest and make the model significantly less interpretable. And this is another challenge that we need to solve on top of this. So to conclude, there are two things that we find out about why people are not using privacy-preserving tools, all over the place. Firstly, they don't have those tools, and it's very difficult to implement them because they're really challenging, very involved. But also, it's very difficult to actually give them a reason. You need to reward them for their participation, or you need to encourage them to share data, etc., etc. Not to mention that it does contradict some of the explainability methods as well. And that's kind of it for me.
Wonderful. Thank you. Any question? I think we probably have time for a question. Then I'm going to ask you for a challenge that you want other people to solve here.
Right. Oh, that's actually a pretty difficult one. So
you can change them later.
Okay, right. Then which specific aspects of trustworthy AI you would rank higher than the others?
Wow, okay.
And why?
Do you rate higher? Okay. Wonderful. Thank you so much, Dmitrii. Wonderful. Thanks a lot.